Okay. So I have posted solution to homework 8 on Canvas. You can find it in the files. The solution to homework 7 will be posted later this week once everyone submit their homework submissions. So let's finish the last lecture today. It's about joint Gaussian PDFs. So last time we talked about this joint Gaussian PDFs. So we define for two random variables with zero mean, we say they are joint Gaussian if their joint PDF can be written in this way. This is kind of a standard form of joint Gaussian random variables with zero mean. Okay. And this parameter rho corresponds to the correlation coefficient. You can compute this correlation coefficient by following the definition using this joint PDF. And you can check that this rho is indeed the correlation coefficient. And moreover, so this part shows that if we marginalize this joint PDF, both of these marginalized PDFs, the PDF of Y and PDF of X, both of these two random variables, they follow a standard normal distribution. Okay. So this rho only characterizes their correlation coefficient. But for each of them, they are always standard normal Gaussian random variables. And because they are standard Gaussian random variables and have a unit variance, so the covariance is actually equal to the correlation coefficient. Okay, and this is how we calculate the covariance between X and Y by following the definition. So here we are using this characterization of the covariance is the correlation subtract the product of the mean. But in this case, both of these two random variables have zero mean, so this part is zero. So we only need to calculate the correlation part. And because we know the joint density, so this is just a standard calculation. So it's a double integration of X times Y, and also multiplied by, this is a joint PDF of X and Y. And then dx dy over the entire space, because the joint Gaussian spans over the entire space. But here, to calculate this double integration, we move all the terms that depending on X inside. Right? So the inner integration only depends on something on X. And for everything about Y, we put them outside. So that is the outer integration. And then by doing so, you realize that the inner integration, this part is a standard Gaussian, it's a Gaussian PDF with mean rho times Y and the variance 1 minus rho squared. Okay, this is a standard form of Gaussian PDF. So this is a sigma square. This is basically the sigma square, and this is the mean. So basically inside this big parentheses, we are basically computing the expectation of X. Right. So inside X, now this is the PDF. So this is a Gaussian PDF of X, right? So it's X minus the mean divided by the sigma square. So inside, by following this PDF, we can see that such a X follows rho Y 1 minus rho squared Gaussian distribution, right? So integration X fx. So this is the inner integration. This one is basically the mean of x. Right? The mean is rho times y, so equals to rho times y. So basically, you don't have to calculate this integration. Just by observing that this is actually corresponds to the expectation, computing the expectation of x, where x follows such a Gaussian distribution. So it's basically the mean, where the mean is rho times y. So that's why we get this rho times y. And then the rest of the part is everything about y. Now you simplify this part, again, you can write this part as a standard Gaussian PDF. So we have rho integration y square 1 over square root 2 pi. Right, so this is a standard Gaussian PDF. It's a zero mean unit variance. But integration y squared times the PDF dy. So this part, this integration is basically expectation of y squared. Expectation of y squared is basically, in this case, is zero mean. So it's sigma y squared minus ey squared by the characterization of the variance. And the variance is 1 and the mean is 0. So this is 1. So the entire thing is 1. So in the end, you get rho, which shows that covariance is indeed rho. Yeah, so this is a trick that we will need to use by dealing with joint Gaussian, or in the future, many high-dimensional Gaussian PDFs. That is, you don't really have to compute these integrations. You just need to rearrange the terms in a way so that some of them corresponds to a certain Gaussian PDF. And then the integration simply means some statistics about that Gaussian random variable. For example, here, this integration is basically the mean of such a Gaussian random variable. And we can directly see from this PDF formula that the mean is rho times y. Right? So without calculating this integration, you can conclude that it is actually rho times y. And for joint Gaussian random variables, they have a very nice property, which says that if two Gaussians are uncorrelated, then they are also independent. Okay. In the previous lectures, when we talk about uncorrelated and independence, we know that for any random variable x and y, independence can imply uncorrelated, but uncorrelated cannot, in general, cannot imply independence. Now, this is when we talk about arbitrary pairs of random variables. Right? But if x, y are joint Gaussian, if we have this restriction, they are not arbitrary pairs of random variables, but they are joint Gaussian, then independence is equivalent to uncorrelated. Yeah. Now put it the other way, if they are joint Gaussian, then we just need to show that they are uncorrelated. in order to claim the independence. Okay. So basically, in this case, if they are joint Gaussian and also the rho in the joint Gaussian PDF, the rho equals to 0. So the correlation coefficient equals to 0. Then we can directly claim that they are independent. Okay. This is because if you plug in rho equals to 0 into this joint Gaussian PDF, so you set rho equals 0. So this is 0, this is also 0, and here is also 0. Then the joint PDF, this joint PDF evaluated at rho equals to 0 has a very simple form. And this form can be factorized into a product of these two. Well, you can see each term, each part of this product is a standard normal distribution. Okay. So this is basically, this shows that if rho equals to 0, then the joint Gaussian PDF can be factorized into a product of the marginal PDFs. And this is the definition of independence. Okay. So in this case, uncorrelated implies independence when they are Gaussian. And then we can define this so-called conditional PDF, which follows a very similar definition as the conditional probability. Okay. So if two random variables has a joint PDF, then the conditional PDF written as Fy given X. This is just a notation, which is defined as the ratio between the joint PDF and the PDF of the conditional random variable X. So this is the precise definition. Now, following this definition, we can write the joint PDF as a product of the conditional PDF times the marginal PDF, right? So this is a joint PDF. We can factorize it into two ways. One way is we consider Fy given X and then times Fx. The other way is Fx given Y times Fy, right? Either way is talking about the same thing. So this is very similar to the conditional probability rule that we introduced at the very beginning of this course. Yeah. So using this definition of conditional PDF, we can also write the marginalized PDF in the following way. Now, first of all, if we look at marginalized Fx, the PDF of X, by definition, it is a marginalization of the joint PDF over the Y dimension, right? So we're integrating the joint PDF over Y. That will give us the marginalized PDF of X. But since the joint PDF can be written in this way, so we can rewrite joint PDF as such a product. And moreover, if in some cases, if we know their X and Y are independent, then in that case, this joint PDF is actually a product of the marginalized PDF. Okay. And then you plug in this one, you replace this joint PDF with the product, you can conclude that the conditional PDF equals to the marginalized PDF, right? So Fy given X equals to Fy. This is because now what X is independent of Y, so when we condition on X, doesn't matter. So similarly, fx given y is also equals to the marginalized fx. Yeah, so here everything is very similar to the conditional probability. And moreover, if we have the joint PDF over multiple random variables, okay, we can follow this similar way to decompose this joint PDF into a sequence, a product of a sequence of conditional PDFs. So we can start from the first random variable, the marginalized PDF of the first random variable, and multiply by fx2 given the first random variable x1. And also multiply by fx3, but now we need to condition on the previous two random variables. And we keep doing this until we reach xn. So this is a general formula. And when everything is independent with each other, this entire joint PDF can be factorized into the product of all the marginal PDFs. Yeah, and this is when all the random variables are independent, meaning that, remember when we introduced independence of multiple events, right? The independence of multiple events actually means that you pick any subset of the events, they are mutually independent. Okay. So here is the same thing. So here it is, we are not talking about pairwise independence. It is the independence among all the random variables. So if they are only pairwise independent, then we cannot have this perfect factorization. Okay, so these are just some generalizations of this conditional PDF rule to the multiple random variables. Yeah, but most of our examples were based on two random variables. So let's look at this one. So in this example, we suppose x and y are jointly Gaussian with correlation coefficient rho. Okay. Now, given this sentence, we can write down the joint PDF of x and y. Right? It is basically given at the very beginning. This joint PDF. Now, we want to find the conditional PDF of y given x. Okay. So basically, we are given the joint PDF with correlation coefficient rho. So the joint PDF is given this way. And we know that at the beginning of this lecture, we know that the marginalized PDF is a standard Gaussian random variable, a standard Gaussian. Now, given this two, we can compute the conditional PDF of y given x, which by definition is the joint PDF over this marginalized PDF. Okay. Now you just divide these two big exponentials. Okay. So you get this one. And then you can try to simplify this result because this part can be combined together. Okay, so after some simplifications, you can get this result. Okay. So this is if you look at this form, this is another Gaussian PDF. And we can see that this part, these two parts, they are the same. So this is actually the variance part, the sigma square part. Well, this part is y minus something, right? So this part is the mean part. So the entire expression can be viewed as a Gaussian PDF on y, on y. So fy given x. Right. So in this expression, this x, we are conditioning on the realization of x. So this one is given. So therefore, this is a constant. This is the mean part. Well, this one is the sigma square part. Right. So this fy given x is a PDF on y. And from this one, we can see that this y given x, this random variable is actually following the Gaussian distribution with mean rho x and variance 1 minus rho square. Because we are conditioning on the realization of x, so this is a given number. So this is a conclusion that you can use in the homework problems. Okay. You can directly call this conclusion. So if x and y are jointly Gaussian like this, then y given x is following this Gaussian distribution. And similarly, x given y is following this very similar Gaussian distribution, where you just replace x by y. They are symmetric. So you can see if these two are jointly Gaussian, then everything will be Gaussian, right? Their marginalized distribution will be Gaussian. The conditional distribution will be Gaussian. So this is a very nice property about Gaussian. So let's look at the following example, which is a kind of discrete case. So we define capital N as the number of products manufactured by a factory. Okay? So this capital N is a positive integer. Okay? It is the number of products manufactured by a factory. And we assume that this capital N is a random variable with such a probability mass function. And then this x is defined as the value of each product. Okay, so this x is a positive real number. It corresponds to the value of each product. And this value, we assume that it follows a certain distribution, fx. So basically, the number of products manufactured by the factory is a random variable. Okay? And then each product, the value of each product is also another random variable. And then in this case, the total revenue is simply capital N times the cost, the value of each product. So it's capital N times X. And we want to find the the marginal distribution of the total revenue. Okay. So here, this FY, this total revenue clearly depends on two factors. One is how many products does the factory manufacture? And then the second factor is the value of each product. So we have to compute the marginal distribution of FY, we need to condition on these factors. So here is a general decomposition of the total revenue in terms of the total number of products manufactured by the factory. Right? It is basically, if you look at this, this is like a total probability law. So depending on how many number of products the factory manufactured, so this is the probability of the capital N equals to N. So basically, under this probability, we are looking at the case where there are only small n number of products. Now, in that case, we want to compute this distribution of the probability density of the total revenue conditioned on such a number of total product. So given that the factory manufactures this number of products, what is the total revenue? Right? And then we sum over all the realizations of the number of products. Now this could be going from 1 to infinity. So this is like the total probability law. Well, the entire space can be partitioned by these discrete realizations of the number of products. And then we need to look at this one, okay? Because this one is already given. The probability mass of manufacturing small n number of products. This is already given. So let's look at how to compute this conditional PDF. Now, given that we have small n number of products, given this one, we know that the total revenue is basically small n times capital X. So therefore, by the definition of conditional PDF, so Fy given n so here we are utilizing the transformation of random variable functions of random variables. So y equals to n times x. Okay, so in this case, I think we are looking at, so given this condition on this number, y and x, they are proportional to each other, right? Y is n times x, but this n is given. So this is a linear function. It's a linear function. Now, we know the PDF of x. We know the PDF of x, and y is a linear function of x. So we can utilize the transformation, the functions of random variables computing the PDF of function of random variables that we learned in the previous lectures to compute the PDF of y. Right. So here we have x is following this PDF, and then condition on this case. So to make it more explicit, y given n, condition on this case, this random variable y is basically nx. Therefore, the conditional PDF of this random, so the conditional PDF, which is the PDF of this random variable, is basically the PDF of this random variable. And then here you can utilize the fundamental theorem. This is a very simple, y is a simple linear function of x, right? So you have unique root, and we are given the PDF of x. So you can call the fundamental theorem to compute the density of y. Okay? And this is what you get. So this absolute value of a corresponds to the derivative of this linear function. And taking the, remember in the fundamental theorem, we have a absolute value of the derivative on the denominator. And this is the fx evaluated at root of this equation. So this is exactly the fundamental theorem. Using this fundamental theorem, you can get that the PDF of this random variable is 1 over n fx y over n. So this is the expression for this conditional PDF. And now you plug in this back to the total probability law. So the marginal distribution of the total revenue is written in this way. So the total revenue depends on the number of products that we have, right? And this follows such a distribution. So we need to consider all such cases. Right? And in each case, we need to further consider the total revenue. So given that we have made this many of products, what is the total revenue? And this simply depends on the cost, the distribution of the cost, the value of each product. But this is a linear function. So for this simple linear function, we can utilize the fundamental theorem to calculate this conditional PDF. Right, so this is a case where so y equals to nx, where we have n is a discrete random variable, but x is a continuous random variable. So that's why it's kind of a mixture of discrete sum and conditional PDF. And since we have defined this conditional PDF, it is a valid PDF function, right? So we can further define the conditional expectation. Okay. So we can define the conditional expectation of a random variable y given a realization of another random variable x in this way. So we write it as expectation of y given such a realization of x. And to compute this, so this conditional expectation is defined as the following integration, which is very similar to the standard expectation, but we are just replacing the the PDF in the standard expectation by this conditional PDF. Right, so for expectation of Y, it is given in this way. Right, we are using the marginalized PDF. But now for this conditional expectation of Y given the realization of X, it is defined as Y. Still, we are computing a certain expectation on Y. So it's still we are integrating Y times, but we are conditioning on X. So we need to weight each realization of Y by such a conditional probability density. Right. So the small x is given. So here, this one's given. So this density will be something, depending on x. Will be something depending on x. And then we are integrating y times such density over all the realizations of y. So this is a definition of conditional expectation. And we can also define the conditional variance. Right? So basically, we can treat y given x as a random variable. Right? We can define this expectation. We can define its variance, all those kind of statistics. So the variance of y given x equals to small x, and essentially following the definition of variance. So I view this as a random variable. So I'm looking at the deviation. So it's y minus its conditional mean. All right, this is a deviation from the conditional mean. Then I'm taking the square, and again, evaluate the expected deviation, expected squared deviation. Of course, we need to condition on this realization of x. Right? So it's very similar to the standard definition of variance of y, where we just replace all the expectations by conditional expectations. But this expectation is conditional, and the outer expectation is also conditional. And following, if you expand these terms one by one, and you can check that this term can be decomposed into the second moment of y, the conditional second moment. Right. This expectation of y squared, the conditional expectation of y squared minus square of the conditional expectation. So everything is conditional. So this motivates us to think about if we can treat this conditional thing as another random variable, right? Because everything looks like this guy can be viewed as a kind of random variable, because we can define its mean. In this case, it's conditional mean and the variance. In this case, it's conditional variance. And this is indeed the case. So we have this very interesting result. For any random variable x with a PDF, the conditional expectation of y given x is a random variable, is another random variable, right? So this is the conditional expectation of y given x. This thing can be viewed as a random variable. So basically, this conditional expectation is a function of the random variable x. So we write this as something of random variable x. So why can we do this? So how to understand this? This is just a notation. Okay? So you need to argue that this is indeed, following the definition, this is indeed something depending on x. Because we know x is a random variable. Okay? So we just need to argue that this is something, this can be viewed as a function of the realization of random variable x. Now from this definition, we can already see that this is indeed the function of x. Because following this definition, once you condition on a certain realization of x, it will affect your conditional PDF. And when you, after you compute this entire integration, you are integrating over y, so y goes away. So this result, this entire result will depending on something on x, on this realization x, right? So in the end, this entire conditional expectation is a function of small x, of your realization x. Right? That's why here we define it. We write this conditional expectation as phi x. It's a function of the realization of x. But depending on the specific realization of x that you are conditioning on, this thing, this quantity, this real number is a function depending on this realization. Now, if you change this realization to different realizations, this will also change. So we can, in general, we can just say that, okay, if I drop this realization and only consider the random variable itself, it is indeed a function of the random variable. Right. So this number, so this is indeed a random variable. The randomness comes from the randomness of x. Okay. Depending on different realizations of x, you get different conditional expectations. Okay. So this is indeed a random variable. So this conditional expectation is a function of your conditioned random variable, and therefore it is another random variable, phi x. Right. So as an example, previously we have shown this: if x and y are jointly Gaussian with parameter rho, we want to find we want to characterize such a random variable. Right. And because of this,
they are joint Gaussian, so the marginal distribution is always a normal, standard normal distribution. Okay? And from the previous example, we have calculated that when we condition on a specific realization of x, y given this realization follows such a Gaussian distribution. Okay, so the mean depends on this x, the realization. A variance is a constant. And therefore, following this one, we can say that, okay, so we know this PDF, right? So the mean, the expectation, which is the mean of this PDF, is basically rho times x, right? So this conditional mean, conditional expectation is rho times x. Therefore, this phi x, right? This is essentially this phi x. Phi x defined as this conditional mean is rho x. And you can see indeed, this conditional mean is a function of x. It's a function of the realization of x. From here, you can conclude that this, if we drop this realization, right, this, when this x is random, right, this is a random variable. And in fact, it is expressed as rho times the random variable x. Right? And this is the expression for this phi x. So this shows that this conditional expectation is a random variable, right? And in this case, it is simply rho times x. And because x follows the normal distribution, so rho times x follows such a Gaussian distribution. So therefore, we can actually compute the PDF function of this random variable. Okay, we can compute the PDF function of this random variable. So here I should emphasize that, you see, these two conditional expectations, they are, see, the notations are different, right? In this one, we are conditioning on a very specific realization of the random variable x. Right? So if you write it in this way, it is a number, a real number. And in this example, this real number is given by rho times the realization of x, which is indeed a real number. But if you write it in this way, well, you ignore this realization. This means that you are conditioning on something random. Okay, that because you are conditioning on something random, so this entire notation corresponds to a function of the random variable x. Okay, so this is a random variable. Okay, this is a random variable, and this is a realization of this random variable. Right. So you can, so for example, this is a random variable, and when we write it in this way, we say that this is a realization of this random variable. Right. Here is a similar thing. This is a random variable on x. But when you condition on a specific realization, then this corresponds to a realization of this random variable. Okay, so these two different notations needs to be clarified. Okay, so this is a random variable. Okay, whenever we write this, it's a random variable. And following that, we have a very interesting result called the law of iterated expectation. Okay. Let's look at this one. So for any random variable y, okay, we can compute its expectation if we know the PDF or the PMF, right? But here's a very interesting thing. So we can write expectation of y in the following way. Which we call the iterated expectation. Right? So inside, we are looking at expectation of y given x. And outside, we are taking expectation. So okay, this looks very confusing. So let's look at these terms one by one. So this is very clear. Right? We have random variable y, we can compute this expectation given the PDF, for example. Now inside, as we talk about as we discussed before, this thing is a function of x, right? So if we ignore this notation and view it as a function of x, then this is a random variable. And we are taking expectation of this random variable. So you can say this is basically the expectation of phi x. Well, phi x is defined as this random variable. And also, these two expectations, they are taking care of different parts of the randomness. So more specifically, this one here we are taking expectation over, suppose we set a realization of x. And here the expectation is taking over y given this realization. Because we are using, in the end, we will be using the conditional density. We will use this density to compute this conditional expectation. And because inside it depends on x, right? Inside it is a function of random variable x. So the outer expectation is actually taking over x. It's inside is a function of x, random variable x. So the outer expectation is taking over the randomness of x. Okay. So if you see, now you think about this, outer expectation is taking over the randomness of x. This means that once we start from outside and we move inside, once we move to the inner part, we are conditioning on a specific realization of this random variable x. Once we have that specific realization, we can compute the inner expectation part by leveraging this conditional PDF. So the inner expectation, once we fix a realization of this random variable x, from this outer expectation. Once we fix that, the inner expectation will be taking over the randomness of this y. Okay. In this case, the randomness is y conditioned on this realization of x. Okay. Now let's look at the proof of this one, which is not, this is very simple, and this will actually help us to understand this iterated expectation. So expectation of y, of course, it is defined as this integration where we use the marginal distribution of y. Okay. Now, for this marginal distribution of y, we can replace it by this entire integration in this red rectangle. Okay. Because here is basically the joint distribution, right? This part is basically fxy. Right, this is a joint distribution. Joint distribution marginalized over x, we get fy, right? So this is indeed fy. We're just decomposing fy using the conditional PDF and marginalization. And then this will give us a double integration. So we have dx, dy. We can exchange the order of integration to dy, dx by rearranging the terms properly, right? So if you do that, here we are doing inside this integration, we are integrating over x. But when we exchange the order, so inside we will be integrating over y first. And then this integration will be, in this integration, we will collect all the terms that depend on y. And this, if you look at the definition, is exactly the conditional expectation. It is conditional expectation. So this is basically the phi x. Well, this is a small x because we are conditioning on this realization of the random variable. So it's integration phi x fx dx. Right? So it's exactly the definition of the expectation of this phi x. So it's the expected value of this phi x random variable. But this phi x random variable, we write it in this way, right? Phi x is denoted as, this is just a notation. It's expected value of y given x. This is a random variable. Okay. So from this integration, you can see that the outer expectation, this one, it corresponds to the outer integration. So the outer expectation is handling the randomness of the random variable x. Right? So that's why here we commented that this expectation is over x. Once we fix a realization of this random variable x in the inner expectation, in this part, we fix a realization of x, and we are handling the inner expectation is to handle the randomness of y given x, right? So the inner expectation is the expectation of y given x. And depending on different realizations of x, the inner this conditional PDF will be different. So that's why we write, in general, we write EY. No, basically, of course, this expectation is taken over y, taking over the randomness of y. equal to EX, y given X, y given X. Right. So this is called iterated expectation. We have one example, two examples to illustrate the importance of this iterated expectation. In fact, we have been using this concept in the previous, many of the previous problems. So let n denote the number of coins picked from an infinite collection, Poisson lambda. Okay, so n is the number of coins picked from an infinite collection, but it is modeled by a Poisson distribution. I'll put it the other way, n is a random integer, positive integer, whose probability mass is given by the Poisson lambda distribution. Okay. So following this distribution, we will draw this number of coins. Okay. Each coin turns head with probability P independently from others. So everything is independent. Okay. And it's also identical. Each coin turns head with the same probability. So we call this IID, right? Independent, identically distributed. Simplest setting. Now, let K denotes the number of heads observed from flipping these n coins, a number of coins. There are two things, both n and k are random, right? The number of coins that we draw are random, following a Poisson distribution. And then once we fix that, the number of heads observed is another random number. So we want to find these two expectations. One is given, we want to find these two, right? Well, this is a random variable, and this, okay, is a number. Because we have expectation of k is a random variable, so expectation of k is a number. Right? Now this notation means it's a random variable of capital N. Right? So first of all, Poisson lambda is given as this one. So we know the probability mass of capital N. Okay. This is how you determine the number of coins that we draw from this infinite collection. And for this K, if we fix the number of coins that we draw, then this K, the probability of K is very easy to compute. It's a binomial distribution. Right? So given condition on n coins, if we have small n coins, then the probability of observing small k heads is given by this distribution. Right? Well, this k range from 0 up to small n. Okay, cannot exceed this total number of points. Yeah, this is when we condition on the number of coins that we draw. So for this one, to compute this random variable, to understand this random variable, we can first understand this number, where we fix a realization of n first, and look at how this number is computed, right? So again, once you fix the realization, this is a number. This becomes a number. If you don't fix it, it's a random variable. Right? Okay, so this this term means that given that we have n coins, what is the expected value of the number of heads we observed? Well, we already have this PMF, so it's basically the mean of this distribution. Given we have n coins, what is the expected number of heads? Right? So here you can either, if you know this is a binomial distribution, you can directly conclude that the mean value is NP. Right? But here I use a decomposition method, decompose the binomial into a sum of Bernoullis, where each Bernoulli has a mean P. Okay, so it's two different approaches, but I think we can directly conclude from here that this is basically NP. So you can see if you fix a realization small n, you get small n times P, right? So therefore you can conclude that in general, if you don't fix it, it is basically this expectation is capital N times P, right? So indeed, this is a random variable, which is a function of capital N. It's a function of the random variable capital N. So this is such a random variable, okay? E expectation of K given N. Now, expectation of K is a number. To compute expectation of K, we can leverage the iterated expectation law. Because we know K, this K is observed by flipping the n coins. So this K is depending on N. Well, N is drawn from this Poisson distribution. So very natural idea to compute this expected value is to consider using the iterated expectation law to first condition on this capital N and then taking the expectation over N. Right. So we have just shown that condition on this random variable N inside this conditional expectation is N times P, is here. Right. So it's a random variable N times P. And then given that, we just need to compute such expectation. Well, N follows a Poisson lambda distribution. And by the linearity, this is P times expected value of N. And we know that for Poisson lambda, the mean is simply lambda. So in the end, it's P times lambda. So you can see that this one is indeed a number, right? Because it's like we are taking expectation of a random variable. But this one is still a random variable because we are still conditioning on something that is random. So it is still a random variable. But this one is a number because we are conditioning on something fixed. This is fixed. So indeed it's a number. So the overall idea is to observe that K depends on N. So we first, to compute the expectation of K, we first consider condition on N, and then taking the expectation over the randomness of N. For this example, we have a bunch of IID random variables with the same mean. Okay. IID means identically, independently distributed. And here, N is an independent positive integer. So N is a random variable. And it takes positive integer values independently from these random variables. Okay. And for this random variable N, it has finite mean. We want to find expectation of this sum. If you look at this sum, it's a summation over all these random variables. Okay, so there are two randomness here. First of all, for each xi, it is a random variable. Okay, and all these xi's are independent from each other, but they follow the same distribution. The second of all, the number of xi's involved in the sum is also random. Okay, this upper bound n is also a random integer. So we need to compute this for this random variable z. We need to compute this mean. Now, if you write it down, e of z. Now z is this summation, so it's expectation of this summation. Okay. And here you cannot apply the linearity of expectation, right? Maybe before that, a very simple idea is because this is a linear form, so you may want to pull this summation out of this expectation. But this summation involves something random, so you cannot pull it out. So this is the tricky part. Once you fix this one, you can pull it out. So to compute z, we realize that we have to, this z really depends on how many of these xi's are involved. So we have to leverage this iterated expectation. First, consider conditioning on this capital N, and then later on, we can take expectation over capital N. So let's do that utilizing the iterated law. We get this one, and z is this sum. So z is this sum. Now, looking at the inner expectation, condition on n, this capital N is fixed, so we don't need to worry about the randomness of n anymore. Okay, so therefore, for the inner expectation, we can pull the summation out of the expectation because we are conditioning on n. So this is no longer random anymore. We can pull it out. So it's a sum of these conditional expectations. But we know that capital N is independent from these xi's. It is given in the problem statement. So this n is independent from xi. Therefore, it can be removed. So we only need to worry about the sum of these expected values of x. We only need to worry about sum of expected value of xi. And for each xi, we are given that the mean is ex. This is just notation, but it corresponds to some number. Okay, so the mean of xi is simply ex. So we plug it in. So it's sum of ex. Well, this ex is a number. And apparently this does not depend on I. So sum of this ex is simply capital N times ex. And we know that ex is a number, so it doesn't depend on capital N, so we can pull it out. So this is a universal constant. So once we pull it out, ex, what is left is the expectation of capital M. Okay. So in the end, we conclude that the expected value, the expectation of this random variable z, is given by the product of the expectations of these two random variables. Right? So indeed, this is a number. E of z is a number because the expectation of xi is a number, and the expectation of n is also given as a number. These are two numbers. Right. So this shows that when we compute something, when we compute the expectation of something that depends on some other random variables, we can utilize this iterated expectation law. So basically, inside, once you condition on this random variable, you no longer need to worry about the randomness of capital M. Okay, that's why here, once we condition on N, this part can be treated as a constant. And then we can pull it out by the linearity of expectation. Yeah, and the randomness of this capital N will be later on handled by the outer expectation. Yeah. Okay, I think that's everything about lecture 19, and I think we can, you guys can work on homework 7, homework 8, and make sure you still submit homework 8 before Sunday night. Okay. And then next week we will have midterm 2, starting from Wednesday to Friday. I will upload the paper to the Canvas, to this page. You work on that and find us 2 or 3 hour time slot working on that, and then submit to the Canvas. I can try to grade it over the next weekend. Okay, I will see you in the office hours at 1 p.m.